Anyway, all right, we're recording, so let's take a look at these problems. So the first one, I redrew it in a way that I find is easier for my students to figure out what the products are. But you notice we started with an E dienophile, and so our product is going to be trans in our six-membered ring. So let me just draw the product. So we have our six-membered ring like this. We formed a pi bond here, and we're going to have one of those ketones going down. The other one is going to be coming up like this. So they would be trans to one another like that. All right, for the next one, I'm not going to redraw the alkyne. I'm not going to rotate it 90 degrees. I'm just going to leave it the way it is. And so we're going to form a sigma bond here. We're going to break one of these pi bonds and make a new sigma bond here, and then we're going to put a pi bond here. So when we do that, hopefully I can find some room to squeeze the product. It's going to look like this. We have our six-membered ring. We'll have a double bond here. And then both of these carbons where the ketones are attached, both of these are sp2 hybridized. And so they're not up or down. They're just in the plane of the screen. So there's our product in this case. The next one, again, same vein. We just draw sigma bond being formed, another sigma bond being formed, and a pi bond being formed. And so we end up with a product that looks like this. Now this one's going to be bicyclic, isn't it? Because we've got our six-membered ring, but then we have a five-membered ring that's going to be attached to the six-membered ring like this. And so since the dienophile, that five-membered ring, is locked in a cis conformation, that means that both of these bonds are going to have to be going up or down. So it's kind of hard for me to draw it now, but let's just say this one's going to be going up, and then this one is going to be going up, something like that. Right, so they're going to be cis to each other. Put our double bond in there, and there we go. And then the next one is again in the same vein as D, where if we draw our curved arrows, form a sigma bond, form another sigma bond, put our pi bond here, and in that case we end up with another six-membered ring. We have a double bond here, and then we have our two nitrile groups like that. There you go. So that's kind of your introduction to drawing Diels-Alder mechanisms with dienophiles, whether they have double bonds or triple bonds, and then whether the double bonds are locked in a trans or E conformation like in C, or if they're locked in a cis conformation like in E. So with that in mind, it says here that recall that many dienes can exist in the S-cis or the S-trans conformation. And you'll remember I told you that the S stands for sigma, and we know that a sigma bond can rotate, right? It can freely rotate. And we said that there's a barrier of rotation between the S-cis and the S-trans because you have to break the orbital overlap between the p orbital here and the p orbital here. But anyhow, that's neither here nor there. But the idea is that the Diels-Alder reaction can only happen, you only get a Diels-Alder reaction when the diene is in S-cis conformation, okay? The Diels-Alder is never going to occur when it's in the S-trans conformation. So if you take a look at this diene right here, you might think, well, that's a nice diene. Yes, it is. However, it's trapped in the S-trans conformation, right? You can see how, right? There's no way you can rotate that to get it into the S-cis conformation. And so you can mix that with a really good dienophile like this compound here, but there's not going to be any reaction whatsoever because carbons 1 and 4 are too far apart. However, what if you have your diene locked in a five-membered ring? So if you look at cyclopentadiene, you can see the diene is locked, right, in the S-cis conformation, right? If S-cis is like this when they're next to each other, you see they're tied together, so it's stuck like that. So that means that cyclopentadiene is actually an extremely reactive diene. You can put it in the presence of almost anything and it's going to react. But since in this case, your diene is cyclic, right, you end up forming a new ring. So you end up forming a bicyclic compound, and this is a bridged bicyclic compound. So this is a bridged bicyclic. Okay, and you notice that your dienophile is in the trans or E, doesn't matter. It's an E conformation. And so you end up with one of the groups pointing up, okay, and another one of the groups pointing straight down like that. And of course, you'd end up with the enantiomer, the non-superimposable mirror image as well. All right, so with that in mind, it turns out the cyclopentadiene is actually so reactive that if you have a bottle of cyclopentadiene, it's going to react with itself, right? You've got the diene here, and then you've got a dienophile trapped in a molecule like that. So it's going to do a Diels-Alder, right? Your same old Diels-Alder reaction like this, and you end up forming this tricyclic compound called dicyclopentadiene. Well, if you're wondering, well, if it just reacts with itself, then how can you have a bottle of cyclopentadiene? What would you have to do? You'd have to heat it up above 200 degrees Celsius to do the retro Diels-Alder, and that would isolate some of the cyclopentadiene like that. So that is how you would do it. All right, now with these three dienes, it asks us to rank them in order of reactivity in a Diels-Alder reaction. So we're going to call this one A, this one B, and this one C, and we'll go from most reactive to least reactive. We'll start with the least reactive. Can anybody tell me which one of these would just be the least reactive? It's not going to react in a Diels-Alder. It just won't happen.
A?
Absolutely, yeah. Hey, big time, right? So we'll put A down here. Why? Because it's locked in S trans. Kristen, I think that was your voice, so thank you. All right, could anybody tell me which one is the most reactive? Which one's locked in an S cis?
B?
Absolutely. There you go. So we'll put here locked in S cis, so you don't need my help with that. And then you see that C is in some kind of no man's land, right? It's somewhere in between because you can rotate that sigma bond, right? And then you could end up with something that looks like this, where you have the S cis conformation. Okay, you'd have something like this and something like that. It's just there's going to be some steric hindrance here maybe, but that's going to be reactive to some degree. So we'll put C somewhere in the middle like that. All right, so going back to this whole idea of when you form the bridged bicyclic product, you can have positions or groups pointing up like these two protons that I'm drawing right now, or down like these two protons that I'm drawing right now. If the protons or whatever groups are pointing in the up position, we call that exo. So we say that these are in the exo position, these two aldehydes. And if they're pointing down, we say that's the endo position. Hold on, just give me 1 second here. Sorry, you guys, can we take another short break here?